So the title I eventually called it was Networks Integrating Energy Systems, and we'll find out what I mean by that in a minute. So, I mean, we're all very used to thinking about ourselves as individuals. Many of you doing PhD, well, that's clearly the case. And we imagine ourselves working alone and working in our own discipline. Okay, so in energy, we often think about it in this way as well. We think about resources or converters or generators or storage on systems and all the rest as separate things. Okay, they're intrinsically separate. And in practice, that's not true. All of these things are all part of the same big continuum, and they're all linked by physical or economic or social networks of some form. So we'll use that word in a very, very loose sense. And the upshot of that is that looking at things in isolation means that you often either miss the point, or you often miss the impact of other parts of that wider system on your bit, if that's the way to think. So there's the whole important to think about this from a personal point of view as also a sort of disciplinary view. So I'm going to pick up on this and try and illustrate some aspects of this using renewables integration, and you'll hear about this a lot here. It's one of the things that we do, and I think it's one thing that runs right the way through all of our work. And we'll all be very familiar with the reason for looking at renewables: well, lower CO2, lower fossil fuel use, jobs, etc., etc. But one of the things that's really obvious from this is that you can't just do that in isolation. You have to think about the system as a whole, and actually having something which is physically and economically capable of absorbing those renewables when and where they're produced. Now, the mainstream media is something that I tend to sort of pick up occasionally and largely laugh at, because often the risks seen by renewables are massively overplayed. So if you pick up a typical edition of the Daily Mail, it will talk about cancer, renewables and house prices, and if it can find something that does all three, then it's got to be a great story. More often than not, it's rubbish, and more often than not, it is plain unhelpful in terms of what we're trying to do. But I think the key thing, certainly we're talking about renewables, is there are underlying challenges with them relating to where they are, and particularly to their variability in space and in time. And there are particular issues about the extent to which you can depend on them at peak times or whenever that might be. So I think fundamentally there is a challenge with renewables in that if you want very high penetrations, it's going to be very hard to do that, particularly if you're simultaneously trying to decarbonise your heat and your transport. And one of the main ways that people have thought about this in recent years is by electrifying both of those systems. So quite a challenge. So the things that people think about doing is that you have a nice spread of renewables in space. You get some quite nice geographic diversity effects that tend to smooth each other out. If you have different types of renewables, you get the same effects. They tend to sort of, when one is high, the other is low, and that's certainly with solar and wind, that seems to work quite well. Wave and tidal and hydro obviously will fill in on the top of that. And there are a range of solutions, if you call that, that people talk about when they're talking about renewables integration and how you can integrate more of them. And they tend to fall into four main areas. One is storage. Some see it as a sort of silver or magic bullet for dealing with intermittency. I don't think it is a complete solution. Interconnection, so between UK, Ireland, UK, Denmark, wherever, a solution or a partial solution. Also, the ability to control demand in some way is seen as helpful. In that way, you can try and, rather than matching generation with demand, you do it the other way around. And also having some sort of flexible generation that fills in when renewables aren't there and follows them up and down. I think in practice, the way that you're going to get at this is a mixture of all four of those. But you'll notice that all of those really are quite electrical in nature, and they are, in many respects, quite expensive from that point of view, certainly when we talk about storage. There are alternatives to doing that, and one of those alternatives is to exploit the fact that we don't just have an electricity system, we have a series of parallel energy systems. So we have a gas network, we may eventually have a hydrogen network, and we certainly have heat being required at many places. In some cases, we have heat networks. So are there opportunities and risks that arise from starting to think about using those alternative energy vectors as a means of assisting us in terms of boosting the opportunities for renewables? So what I'm going to do in most of the rest of this is talk a bit about a piece of work that we did about gas and electricity systems, and particularly how those gas systems were affected by wind generation. So it's one of the early pieces of work in this area, and certainly a very unusual bit of work, and I think quite a good bit of work. So the work that I'm going to talk a bit about is by James Whiteford, who's a postgrad here until about 2012. He currently works for National Grid, and the work that he undertook was part of a project called Ampères. There's only a bit of gas work in that project, and it was sponsored by National Grid and also Advantica, which became Germanischer Lloyd, which became Germanischer Lloyd DNV, or something. What it will be next week, I don't know. And what the work was trying to do was try and understand how the gas system talked to the electricity system and how it would handle an increasing penetration of wind, and also a sort of shift away from coal towards more combined cycle gas turbines. And it was very unusual in the sense that it looked from the position of the gas grid. A lot of the other work that you see in this area is very much electrical focused. It's very much from, well, the gas grid's a thing and we'll worry about it. It was the other way around with this one. And it looked from the position of the system operator, which happened to be National Grid Gas, and how the national transmission system for gas worked in tandem with the electricity system. So it had a very deliberate focus, and what we were constrained by was a set of tools which were available to National Grid Gas, and which they planned and operated and dispatched their system with. So what we were looking for was gaining an understanding of how the gas system operator would view and could visualize wind generation in the electricity system, and how that would feed through into their gas system operation. So one of the things that's very important about this is that the gas and electricity systems are separate. Okay, they are interconnected at different locations, but legally and operationally they are separate entities, despite the fact they're owned by the same holding company. But the two parts of the company are not really supposed to talk to a great extent unless authorised. So the key thing here is those systems are not operated in tandem, and they're certainly not co-optimised. So they're separate things and they do their thing. So one of the upshots of that is that the system operator on the gas side doesn't have a detailed view of what's going to happen on the electricity side. So it doesn't have a detailed view of what wind is doing, and it doesn't have a detailed view of what the gas generation is doing or would be doing in response to wind. Another aspect of this work is that there are a range of technical standards, like there are in electricity, a range of technical standards which govern the design and the operation of these systems. And one of the important ones of that is that the gas system, because it's so complex and it's based around fluid flow, one of the requirements is that they must use models to design and operate the system which are very, very close to reality. Okay, there's no noddy models with this. It's pretty much the full system model. So anything you do with that, you have to use something approaching the full system complexity. And one of the interesting bits about that is, rather than modelling, say, a compressor, which is key to that, as a simple pressure raising device, you have to model the whole compressor. Okay, so that involves the various flow rate constraints, surge and choke. So there's some mechanical engineers going, I've heard of that. So it's a mechanical system. And so you need all of that information in your model. And another aspect of this is that gas systems have quite a slow time constant. Electricity systems, it's almost instantaneous. In gas, it takes time to physically move the gas from one end of a pipe to another. So there's quite a slow pattern to this. So the way that the gas companies operate their system is they employ something called transient analysis, which actually factors in the full mechanical flows of gas down the line. So it takes in momentum, energy, mass transfer. And that's a pretty challenging thing. In addition, one of the advantages of the gas system is you have some inbuilt storage in the form of line pack, and that's basically an ability to squeeze a bit more gas into the pipe than you normally would and then draw it down a bit. So it basically gives you a buffer, a pressure buffer to swing between, and that's used extensively in operation. And the reason the transient analysis is important is because if you're talking about a system where you're ramping up generation up and down in response to wind, then you're actually talking about potentially quite big swings in gas flows and gas pressures during the day in response to wind. Now, some other work, particularly in Cardiff, has had a sort of quasi-transient, so essentially a sort of series of steady-state models which they claim do this. I've never actually seen any analysis to see whether that's actually true. So there's still, I think, there's still an assertion about whether that's realistic. Certainly, in terms of the sort of realistic complexity, I don't think, other than National Grid, I don't think anybody has ever tried to do this at the scale that we did. So one of the bits of the analysis as well, we were very interested in the contractual arrangements that the system operator has, and a lot of that is about defined pressures in the gas system that they must maintain. So the way that James thought about doing this was, he was very interested in the peak stress days. So that's the very cold days, probably like today, where you've got relatively still, very cold temperatures, high heating demand. Well, that doesn't apply here. And then looking at, well, in those high pressure, those high demand days, what does wind do to the system? So there are a series of different scenarios of supply applied, and then a series of bits of analysis carried on each of those. So the working principle here is that, fundamentally, the gas system operator cannot anticipate a change in CCGT operation as a result of wind. And its working assumption is that the demand for the day is flat. Okay? And in practice, it's not, but that's how it's done. So what this analysis did was tested just how wrong that assumption was, and also whether or not the response of CCGT to wind would result in higher or lower off-takes of gas and higher or lower pressures. So to actually figure that out, there were a range of different models applied to that, and there was a fully detailed transient model of the national transmission system, a relatively detailed model of the British electricity system, and then a detailed wind hindcast applied in a sequence. So I'll pick up a little bit about those. So the first bit I'll pick up is the wind model, and that comes out of the work of Sam Hawkins, and that model is available for anybody to use should they wish. And it's a relatively long 11-year time series, down to about 3 kilometres on an hourly basis, and it does a reasonably good job at simulating both wind speeds and the wider fleet. Relatively low bias on that. So with this particular example, there was a fleet of something like 13 gigawatts onshore and 19 offshore. So what's that? Something like 32 gigawatts overall. So it's a pretty big wind installation, substantially bigger than today. So the idea here was that you had a wind model, you had an electricity model, and then you had a gas model. So the wind model basically sets a series of boundary conditions for the electricity model, and the electricity model essentially dispatches the system as it sees fit. And it uses something called a unit commitment model, so it tries to do it efficiently and as cheaply as possible, but it also tries to capture the requirements for generation to be up for a certain amount of time, down for a certain amount of time, and their ability to ramp between different states. So it's reasonably realistic. It had a rolling profile, so it looked 24 hours ahead, and it assumed that the dispatch was perfect. Okay, it had perfect knowledge. And what that does is that translates into a dispatch pattern for each CCGT, and that then sets its gas demand for the day. And that was in a context of quite a large fleet of mixed fleet of renewables, nuclear, gas and coal. And that basically sets a sort of boundary conditions for the gas system. And here's a bit of colour, here's a picture, which is great. So this is a very big system. Most of the models you see in literature are talking about 30 nodes. Okay, this one is 800 nodes, so it's 10 times larger and many, many times more complex. It also contains a whole range of things in addition to pipes. regulators, which basically will control flows or pressure, a set of valves which give you on-off, and also quite a large number of compressors. So this is a pretty challenging problem to solve even at the base level. And the software that we used was something called Graphical Falcon, which was National Grid's then default package. It's still used by a number of the distribution companies. The problem with it is it requires manual operation. So there's no automation, there's no optimization, and it's somebody sitting there and figuring out how to get gas from here, here, and here to there, and there. Okay, so it's pretty challenging to use, and highly iterative, takes quite a long time, and it's quite skilled. So, the aim here, and certainly by the time that James was doing this analysis, he was working for National Grid, so he was reasonably skilled at using it. So I think it approximates what the system operator would do in those circumstances. So the sort of things that you were having to deal with there were high and low pressures, intakes and offtakes. The offtakes are sort of distribution systems, maintaining differential pressures across different parts of equipment, the whole of the envelope of the compressors, and what you were looking there were essentially soft limits on the line pack. There was a sort of target amount, as well as some sort of reserve. So if you get it wrong, there's a bit that you can either draw extra gas or push the gas somewhere else. So they were just sort of operating margins of the system. And there were 3 runs in this. That's why this diagram is so complicated. So basically, it takes the gas from the CCGT, and the first run, it assumes that everything's nice and fixed. The demand and the gas are fixed over the day. It gives you an initial starting condition. The next thing is it starts to look at varying demand, and the idea here is you run this across the day and you try and set up the system so that it can do that. And what it does is it gives you a base level for the line pack, so a high to low pressure swing that's big enough to meet the needs of the demand. After that, you bring in the variable CCGT, and then essentially it's overlaid on top of that. And the difference between those 2 transient runs is basically a measure of the operational uncertainty that the system operator faces, and it indicates the extent of the changes that need to be made to accommodate the wind on any given day. So as I said before, it's an iterative process. It involves you sitting in front of the computer screen and trying to set the requirements for pressure and flows, and the system will tell you whether or not you're going to get it right. So there's a series of alarms that will scream at you if the pressures are too high or too low, the flows are too high or too low, you're in and out of your compressor envelope. So in a broad sense, it's not optimal in a mathematical sense, okay, but it's close-ish, we hope, to what goes on in reality. So the idea here was you end up with a strategy for a particular setup that's credible, that is feasible in terms of the various flow and pressure constraints, and then if that works, then you have something that's you try and minimise the use of compression. If it doesn't work, that's deemed to be a sort of failure of the underlying system, and then that will force the system operator, in this case the proxy, James, to play about with bringing in additional resources, the operating margins, to try and make up for that. So in practice, if you have done all that and you still can't get it to work, then you've got a problem. And what National Grid do in reality is they will then go back to the market and say, we'd like somebody to turn their demand down, please. And if that doesn't work, then they start manually turning people off. So there's a sort of sequence of events there that kind of mimics what goes on in reality. So the series of scenarios tested, and what they did was they looked at different patterns of inflow. So there are a whole range of terminals around the UK, from the continental shelf, liquid natural gas, and so on. And these different scenarios looked at different combinations of those, as well as how much they had in storage. So there were 5 years of wind that were used for this, and that was run through the unit commitment model to give a series of dispatch patterns for CCGT. And because the gas system is a manual system, it's not possible for us to look at the 5 years in total. So the 10 worst days were pulled out of that, and they were run through the gas model in the way described. The worst days were described as things which had the largest swing in gas demand for the CCGT. Okay, so that was quite different patterns, but essentially what they were doing was if the wind blew harder or less hard at particular times of the day, you would see swings in the CCGT above and beyond what would naturally happen. So we're going to take you briefly through one of these rather than the 6. So this is an example where you have quite an unusually low flow in this terminal here, the Easingen terminal, and that's where the Langeled pipeline comes in from Norway. And that's an interesting setup because a lot of the CCGT in Britain is in the vicinity of that terminal. Now, for this particular situation, we had a wind day which saw wind initially quite high, and then it started to fall and then picking up again. So the gas day is unusually 6 to 6. It's now 5 to 5 in the morning. And what happened in this particular case was that the CCGT response was initially to ramp up and then ramp down in the day. And that was quite an unusual occurrence. And it resulted in quite a large swing in line pack. So this grey curve here is the line pack. What National Grid try and do is have something where the line pack pressure moves plus or minus 10 million cubic meters of gas a day. So here we can see it that the variation is something approaching 40. Okay, plus, from top to bottom, so plus or minus 20. So it's about twice what they would expect at present. So that was in itself was interesting. Probably more interesting was what goes on in the red box, because that's the large ramp up. If you concentrate your locations of your CCGT, you get significant concentrations of either over or under pressure, depending on whether you've got too much or too little gas. Okay, so what you found in this particular case was low pressures in the morning because you're drawing the gas into the CCGT, and then high pressures overnight as a result of too much gas being in that location at the time of the day. Now you would imagine that you would just locate all of your problems there. In fact, what happened here was that particular pattern led to a series of under pressure breaches in this area. So this is the north of London into East Anglia. And what was done in this case was a systematic attempt to repressurize the system, changing some of the compressors around, first of all, in this area, and then systematically working north so that you could try and bring more gas from the northeast and then from Scotland. Interestingly, that didn't actually help. And part of the reason for that is the greater the distance you transport the gas, the bigger the drop in pressure. Okay, so you've actually got a problem there. And what that required you to do ultimately was release gas from this location down here, the Isle of Grain, either by keeping the gas in place later on in the day, but releasing some extra gas early in the morning. So, what that succeeded, it was actually quite a small amount that was needed relative to the overall breach. And that managed to bring the system back into balance. Across the wider scenarios, the whole range of those, and the worst case tended to vary between those ones. So in a lot of cases we had basically looking for stress situations, for example, lower than expected flow into St Fergus, or lower than expected flow into Milford Haven, or so on. What we tended to find is there were quite big differences regionally depending on the situation, and also depending on which kind of swing you got, the timing of that. You tended to get either over or under pressures earlier or later in the day. Now the ones where you had problems north to south, they tended to be less serious. Okay, so if you reduce the flow a little bit from St Fergus, it had less of an impact if you reduce the flow east to west. And the reason for that, if you look at the pattern here, and this is heavily simplified, is that the pipelines tend to go north to south simply because the dominant source of gas in Britain has come from the North Sea through the St Fergus terminal. So coming north to south, it can handle it. But anything where you're changing it east-west, it had more of a problem. And I think that's something that's quite realistic in the sense that National Grid struggle where they get ships being diverted based on the price of liquid natural gas, because they're expecting something and they don't get it. So in all cases, we found that the wind patterns tended to increase the swing in pressure, the line pack, in all cases. And in the vast majority, you needed to have some sort of top-up intervention as a result of that. So one of the things that wasn't carried out in this, but I think was certainly was alluded to, was actually one of the interesting bits about this is if you had some sort of selective reinforcement, i.e. you reinforced either the line or you repurposed or a compressor or allowed it to be bidirectional, then you might be able to get out of jail in these situations. But certainly flexibility, additional flexibility in the gas system would have knock-on benefits for the electricity system. The challenge with that is regulatory, in terms of regulatory terms, that's not possible because they're two separate systems, okay? Which is annoying. So what we were able to glean from this was that if you want to do things which the utilities will believe, you need to use models which they will believe. So this is one such model. Very, very hard to use that efficiently. Certainly in this particular case, it was probably quite extreme. One of the things that does come out of this is that compared to some of the other work with simplified models, we see things in here which we don't see in their models. And the reason for that, we think, is the simplification or the oversimplification of those models leads you to basically miss important aspects. But certainly the uncertainty is an area which is really quite important to the gas systems, and it's becoming quite an important aspect of their work. One of the things that's alluded to in a lot of other work is actually if you gave the gas system some operational oversight of the electricity system or vice versa, then you would get some benefits from that, some synergies, and that would be, I think, quite valuable. How that happens is a different matter. And to some extent, this work, I think, raised as many questions as it actually answered. It certainly has been on my mind a lot over the last couple of years, as we've noticed that more and more of our work has been about interconnection of different systems. So I suppose really bringing this back to IES now, I think it really does illustrate quite an unusual feature of this institute. If you look across at what we do, and if you we have work going on in flexible generation, so in CCGT and also nuclear. We've got interesting work at building level analysis and demand side management. Some of that's thermal, some of that's electrical. We've got some electrical and thermal storage work, which is great. We've got people working in hydrogen on also power to gas. And we've got people working in energy vectors, energy markets and market coupling, as well as some of the work that Sasha and others have done on multi-scale. So we've actually got all the right bits to do really quite useful work. And I think the way that would be most useful if we can do that is if we can exploit the new Centre for Energy Systems Integration, which is a 5-year collaboration between ourselves, Newcastle, and a few other universities. And its role is to try and find ways of coupling systems together in a useful and reasonably realistic fashion. So it's quite different to the way that the UK Energy Research Centre, Wholesome, some of the other sort of whole systems models have behaved. And it offers some quite unique opportunities to get your models out there, if that's the right word. And it certainly gives us a really good excuse to collaborate more closely between not just the networks people, but also the storage people, the generation guys, and also the resource people. So there's a sort of that continuum that we see in IES. I think we need to pull together. So I think, although I'm not expecting you to do it now or today, I think I'd like to give you a little challenge, or quite a big challenge, to think about not just about your work, but also where you might pull your work and draw your work in towards what other people are doing. So there's an awful lot we can do if we actually work a little bit closer together, and hopefully that will give you a very good excuse, in fact, no excuse not to do it. Okay. So anyway, that's me. I know that I'm between you and your beer, so I'm very happy to pull it together there. So, yeah.
This production is brought to you by the University of Edinburgh.